So last week, you might remember, hopefully you remember, we looked at Jacobsville sandstones that run from about Bay de Gris down the east side of the Keweenaw Peninsula down to Baraga. In fact, there's a place along here called Red Rocks, right along the highway. You've probably seen that. That's an outcropping of Jacobsville sandstone. And on the west side, we had the Copper Harbor conglomerates, that cobbly looking rock where the pieces are cemented together. And those are the pieces of an older rock that forms the spine of the Keweenaw called the Portage Lake Volcanics. And remember, those Portage Lake Volcanics were put down in layers from a lava flow at the Mid-Continent Rift. And the top of the lava pool cooled off faster, so it trapped gas bubbles in the upper layer. So we have the bottom layer of these rocks is solid. These are just chips from people pounding on it with a hammer. But the top layer of each of those layers of Portage Lake Volcanics is full of these holes called vesicles. And at first they were just empty because they weren't empty. They were filled with the gases given off by the lava as it flowed up. And then this started about 1.1 billion years ago. But about 1 billion years ago, the plates pushed together and buckled and folded and faulted and pushed up the Keweenaw Peninsula. This is the Keweenaw Peninsula right here. Probably should have bent it up some more. And this spine is running right down the Keweenaw Peninsula. And that's why our rock layers are tilted. And now, notice these cracks. That faulting event cracks and fractures the rock. And, look at the cracks in this rock. All of that allows water to come up from deep inside the earth, deep inside the crust. Water comes up in these cracks and deposits minerals in these holes and in these cracks. And in some places it was calcite, in some places it was copper. It was copper. Now you might say, well, copper doesn't dissolve in water. How can the water deposit it? And that's true. If we just take normal water and drop copper in it, we would sit here for 100 years waiting for that to dissolve. And even then it would only look, tarnished on the outside or oxidized. It would turn green, but the weight of the copper would still be there. It doesn't dissolve in water under normal conditions. But deep inside the earth, the conditions aren't normal. Down there, the water is under pressure from all of this weight pushing down. And if you can put water under pressure, then it won't boil at 100 degrees Celsius. It might not boil until it gets 300 degrees Celsius. Or in Fahrenheit, water boils at 212 degrees. If I put this cup on a stove and heat it up, the temperature of the water is going to rise until it gets to 212 Fahrenheit, and then it won't get any higher. If we put more energy into it, it'll make it bubble more and evaporate faster, but it won't get any hotter. But if we put it under pressure, if I can seal this up, then it can't evaporate. And so the extra energy goes into making it hotter. And that's what's happening deep inside the earth. This super hot water has dissolved copper and dissolved calcium and dissolved quartz in it. And when it comes up to the surface, it cools off and it fills in all of these holes with those minerals. And it fills in the cracks with minerals and all the little fractures that shoot off from that. And the copper country is born. So it's that multi-step process of the lava flows, the vesicles, those holes in the rock, and then the faulting event that cracked the rock layers to provide a conduit, to provide a path for the super hot water to come up from the center of the earth. As it reached the surface, it cooled off and deposited all of the things that it was carrying in those rocks. And in some places, they stuck out to the surface and people discovered it. And the first copper boom in the United States took off. Next time, we will talk about how we get that copper out, or at least how we used to. Have a good day.